class. Class is being recorded. Anyone's ready? Tom, Jay. Tom. Let me see who else. Xinping. Right. Hao. Okay, I have major presenters. Anyone who's ready, go ahead.
I'm doing question 31. A three-person basketball team consists of a guard, a forward, and a center. A. If a person is chosen at random from each of three different such teams, what is the probability of selecting a complete team? Since there are three different teams of 3 person in each team, that's 3 times 3 times 3, which is 27 total players, with 3 factorial total arrangements. So the probability of the event is 3 factorial over 27, which is 6 over 27, which is 2/9. And then B, what is the probability that all 3 players selected play the same position? So from A, we know that there's a total of 27 players, and since 3 players are in the same position, the probability of the event is 3 over 27, which is 1/9.
Only 2 parts, huh?
Yes, only A and B.
Okay. All right, so this is very simple and direct. All right, thank you.
Thank you.
Can you see my screen?
Yes.
So for question 33, a forest contains 20 arcs, of which 5 are captured, tagged, and then released. A certain time later, 4 of the 20 arcs are captured. What is the probability that 2 of these 4 have been tagged? And in this case, we're assuming those 4 came from the same forest. So we know this in the sample space, we have 20, choose 4 for the sample space. And then we know among those 20, 5 are captured. That means 15 are not captured. So we can split those 20 into 2 groups. One group is those 5 are captured. And we want to know the probability that 2 of 4 are captured. So we choose 2 from 5.
Are captured or tagged? Okay. 5 are captured, tagged. Oh, okay. Then released. Okay.
And then we got this. Once we evaluate it, we got this. That's equal to 21.6%. 7, maybe.
I see. Okay, rounded up to 7. All right. Okay, great. Anyone has any questions? Okay, so that's J. Wow, some of you like happy. Now 50% done with your presentation. Okay, who's next? Okay, coming up. Who says, can I hear you yet?
Oh, looks like it cut off on the bottom.
Okay, Tom.
Well, for this problem, we're given a bunch of values for sweets, food, and drinks. And after interpreting what they give us, it was much easier by kind of filling in a Venn diagram.
Let's highlight this. Let's highlight this numbers. Let me. I can highlight it for you. So bistro owner has taken stock of. We have this number orders received on a particular day. 411 person. So you have 411. 411 persons ordered only drinks. 231 only food, and 62 only sweets. 45 had drinks and sweets. Oh, okay. So this gives you this, but not food. 312 had food and drinks, but not sweets. And 11 had sweets and food, but not drinks. 41 customers had all three. However, okay. Then what do you have to do? What's the question?
The problem is one of the values is wrong. So the second half of the problem gives us 3 values for the sweets, food, and drinks. So the first part to solving this question is just figuring out that we are using the inclusion-exclusion principle, where instead of using probabilities, we multiply the probabilities by 1101 to get the number of occurrences, since each probability has the denominator of 1101. And that's, after doing that, we get the union of all three is equal to D plus F plus S minus DS minus FD minus SF plus DSF. That's from an inclusion-exclusion. And so the first part is we add up all the values. So from the Venn diagram, I plugged in all the values where, for example, it said 231 was only food. So I plugged that in for just food 1. And the second part of the problem is giving you a second value, like I denoted it like food 2, where we're trying to plug in the second value to get 1101 as our total, because the first S1, F1, D1, if we take the sum, the unions, we get 1113 occurrences. So we're over the sum by 12, which is 1101. So to get the answer is you take the second value that is 12 lower than the first one, which was S2, which was 147. So the correct figure was sweets 2 for this problem. It was a pretty complicated problem, I guess.
Yeah. Hold on a second. I don't get it. What was the question though?
So it basically gives you a bunch of intersections, and for example, 231 only food is food minus the intersections. And so they gave us essentially every value in the union of sweets, food, and drinks. And the union has to equal 1100 when one orders. But the problem tells us that one of the values is incorrect. So when we actually add it up, we get 1113. So we're off by 12. So we have to test out these 3 values from here. And so after you plug in the second value of sweets, which was this part, the first sweets we got, if you add this plus all the intersections, it's 159. But the second one was 147, which was the correct one, since we were off by 12.
So the problem is with sweets, not with drinks or food.
The problem is
Or
that
it
we
could
don't
be.
know which figure is wrong. So
Yeah, so
it's
it
telling
could
us
be.
to plug in all the values to test which one is wrong. Since we're off by 12, we know that it has to be the sweets, because that was the only one that was off by 12.
How do you know the only thing is off? How do you figure out that? How do you figure
So
out the
after
12 is, yeah.
so after, if you replace this part with 147, we get the correct answer, because we're off by 12.
Yeah, we're off by 12. But how do we know it's off from sweets? Can it be from food or drinks?
You would have to test that by adding them.
I see, but this is just one of it, right?
The question says that only one of the figures is off.
Oh. Oh, okay. So you have seen, okay. So the 12 won't work for food and drink if you test it.
Right.
I see.
So
I got
when
it.
we test the first values they give us, we get 113, but it should be 1101.
Right.
So we over added by 12. So the second figure, which was 12 less, gives us the correct answer. Because then we'll get 1101 total orders.
I see. I see. Okay. But you didn't try the other one. You didn't try so S means sweets, right?
Yeah.
Yeah. Okay. Anyone else has any questions? All right. Thank you, Tom. It's only certain of you like to present. What about the rest of you? Everyone needs to present to get the credits for presentation. Okay, who's going to be the next?
Tom, can you like stop sharing so I can share?
Oh, I could do this.
Oh, okay.
Yeah.
Can you guys see my question?
Yeah.
I don't know what's wrong with my connection, but if I start lagging, can you tell me to stop?
Okay.
Okay. So I'm presenting question 19. Okay. Also, an urn contains 11 red, 4 blue, and 7 balls, while another urn contains 5 red, 3 yellow, and 6 black balls. What is the probability that a blindfolded person who picks one ball from each urn chooses either 2 balls of the same color or 2 balls of colors that are exclusive to each urn? So for this question, it's a bit long. So I even draw out the urns for the first urn. we get 22 balls in total. In the second urn, we have 14 balls in total. Since from this, we know that for these two urns, there's a red and black ball. So from these two urns, we can find a probability of choosing 2 red balls and 2 black balls. They're mutually exclusive, and the 2 balls that are exclusive to each urn will be blue and yellow. So I figure out the probability for like calculating the red balls for the first urn. It would be like 11/22 equals 1/2, and for black ball I labeled as K. So for black ball is 7/22 for the probability for the urn number 1, and for urn number 2 for the red balls is probability is like 5/14, and for the black ball is 3/7. So calculating the probability for like a blind person choosing a ball from an urn chooses the ball of the same colors, you multiply them with the one the same color. For red is 1/2 times 5/14 plus the black balls 7/22 times 3/7. We get a probability of 97 out of 308. Now we go calculate the blue balls and the yellow balls. From urn number 1, the black balls, the probability of black balls is 2/11, and the yellow balls from urn number 2 is 3/14. So to calculate the whole what the question asks for us, we put everything together. But this part, I forgot to say this part. So probably for that blind person chooses 2 balls of the colors that are exclusive for each urn is with the blue balls and the yellow balls together is 3/77. And at last we take the blind person from choosing a ball from an urn choosing 2 balls of the same color and adding 2 balls of the same colors that are exclusive to each urn. We add it up, we get this final answer 109 out of 208.
Nice. Okay, very clear. Yeah, anyone has any questions?
This
Yeah,
one
I don't have any questions.
This question took me a while because like it's kind of a lot of work.
It is, but you did it very clearly.
Yeah, thank you.
You're welcome. Anyone has any questions? All right. Let's see, next one. Okay, Zakia, like to present also. I'll make a presenter, Zakia.
Hi, Professor.
Yeah.
Can you see my screen?
Yes.
My question is 36. 2 cards are chosen at random from a deck of 52 playing cards. What is the possibility that they are both aces? For the total probability that choose 2 cards in 52 cards is 52 choose 2, and there are 4 aces in 52 cards, so it's choosing 2 of those 4 aces. So the probability that they are both aces is 1/221. It's about 0.0452. And for question B, have the same value. It's almost similar to question A, but there are 13 different kinds of value in 52 cards. It's A to K, so we need to multiply by 13. The answer is 1/17. It's about 0.05888, and that's it.
Okay. Yeah. You could for my class you could keep as a fraction. Fraction tells you, you know, the part over whole. We don't have to calculate to the decimal points.
Okay.
Okay, thank you.
Thank you.
That's good. And let's see. So I think we left with how. So Catherine, Jie, Tom, Yingping, Yongxin, oh Zakia and how. Okay.
I'll present 37 from chapter 2. An instructor gives her class a set of 10 problems with the information that the final exam will consist of a random selection of 5 of them. If a student has figured out how to do 7 of the problems, what is the probability that he or she will answer correctly? For A, it's that they have already know 7 of the questions and choosing 5 of them over the 10 questions the instructor gives and choosing 5. I arrived this one at the all 5 problems they will get it correctly. For B, I started know that they have 3 questions that were unknown, and then they were they only know 7 of the questions. 3 were unknown. 3 were the unknown ones. And then the probability of getting at least 4 of the question correct was 7 choosing 4. And then I added up the 7 choose 5. It's questions that they already figured it out as they know, and all over the questions were giving and choose. I got 0.5 half for B.
I see. Okay, at least 4 of them. 4. So 5 of the 4. 7. At least 4 of them. Then 7 out of 5 of them. So why you multiply 3 with the out of 7 choose 4?
Because 3 were the question they haven't know as they haven't figured out the 3 problems from the 10 of them.
So what is the probability that he or she will answer correctly, right? At least 4 of the problems. So at least 4 of the problems. So 7 out of 4 and 7 out of 5. So 7 out of 4 you multiply by 3, you will see there are other 3 problems. No, I'm sorry, I don't get it. Can you explain again?
It's just that just the 7 choose 4 were the questions it's at least 4 of the problems correct.
Right.
And then for 3 of them it's just the questions that haven't been figured out by them. That's
right. So okay, 3. Right. So 10 questions, 3 that haven't figured out. Okay, but then because these 3 only multiply by 7 choosing 4, you didn't multiply any number with 7 choose 5. So what makes make them different?
7 choose 5 were the questions the students have figured out, so I just added.
Right, but why you did not multiply by 3 or multiply by 2? So my question is here, right? Why we multiply by 3 here? Okay, so out of 7 questions they figure out right. But the probability you want to find is at least 5 or at least 4. So it could be 4 or it could be 5. So my thinking was, okay, out of 7 choosing 4 is this much. Then out of 7 choose 5 is this much. So I would add them. So I don't know why multiply 3 with out of 7 choosing 4. Out of 7 choosing 4, out of 7 choosing 4. Yeah, because there are how many ways to choose out of 7 choosing 4, right? That's just out of 7 choosing 4. I'm not getting why multiply by 3. But you will see 3 is unsolved. But what does it to do with this question though? We want to find at least 4 of the problems. So the first one is all 5 problems, right? All 5 problem is out of 7 choosing 5, right? Part over whole, that's clear. B, at least 4 of the problems. So at least 4 means 4 and 5. So why you multiply by 3? Can you explain more, for me to understand? Because B is very similar to A, right? A is all 5 problems. B is saying, either 4, at least 4 means 4 or 5. So why we multiply 3 here? Why we multiply 3 with out of 7 choosing 4? Okay, let's see. Jay is trying to explain. Out of 7 choosing 5 implies 5 out of 5. 7 choosing 4 implies 4 out of 5. Oh, okay. Okay, let me see if I can read. I cannot read on this. Oh, okay. That's a permutation here. So out of 7 choosing 4, then because of 5, right? Out of 5 choosing 4. Out of 5 choosing 4 is 3. Out of 5 choosing 4, that should be 5, isn't it? Then choosing 1 from 3 that doesn't know how to solve. Out of 3 choosing. All right, Jia, do you like to explain more about this? So basically, I think you're thinking about the counting principle. You're thinking about,
because for the sample space, right, we are choosing 10. We are choosing 5 out of 10, right?
Right.
And then we have first case that is because he knows 7 he know how to solve those 7 problems. So the first case is he know how to do all the questions on the exam. That would be 7 choose 5.
Right. So only 7 choosing 5. We don't have to consider the not solved ones.
Case. The second case would be out of 5 questions, he only know how to solve 4. So that would be 7 choose 4. And then you still need to pick another 1 question. And that would be 3 choose 1.
Oh, okay. Hold on. I got it. Okay. Okay. Now it's clear. Who's this? How did you see? Did you? Oh, okay. Yeah, that's actually what How was explaining. So I was thinking about that. I was thinking about 3 in the 10. So in the 10 problems. So 7, they know how to solve it, and 3, they don't know how to solve it. I was thinking about that. Okay, now I understand it. So out of these 7 questions, at least 4 is right. So at least 4 is right, and 1 is wrong. So 1 is wrong could come from 3 problems. That means 3 chosen 1. Okay, that's clear. All right, thank you, Jay. Okay, great. Okay, Zakia and Aret. Let me make you presenter. Okay, everyone, just make sure you're following and make sure you ask questions because I think everybody's choosing different questions, right? I assume.
Okay.
Yeah, Zakia.
Yeah.
Yes.
So I'm presenting question 28. An urn contains 5 red, 6 blue, and 8 green balls. If a set of 3 balls is randomly selected, what is the probability that each of the ball will be of same color or different colors? Repeat under the assumption that whenever a ball is selected, its color is noted and it is then replaced in the urn before the next selection. This is known as sampling with replacement. So from the above information, we get total balls is 19 and number of possible ways for selecting 3 balls out of 19. Three balls out of 19 is and 19 choose 3 ways, and so we're gonna do same thing for 3 green balls. I'm sorry, for green, red, and blue balls. So we're gonna choose 3 from 8 for green, 5 choose 3 from red, and 6 choose 3 based from blue. So probability of same color, selected 3 balls are same color. We're gonna add them. 5 choose 3, 6 choose 3 plus 8 choose 3 divided by the total number of possible ways for selecting 3 balls out of 19. Yeah, and then
Okay.
question B. Yeah, you have any question, Professor?
Not really.
Okay.
Yeah, that's B.
So question B, probabilities for 3 different color balls. So we have probability for red ball is 5. The total for red ball is 5 over 19, and blue 6 over 18, and for green 8 over 17. And number of ways that the 3 different balls is 3 factorial, which is 6. And we're gonna multiply all those probability with the 6 ways to get 3 probability of 3 balls of different colors. Now they ask for the last part of the question. They ask for sampling with the replacement. Whenever a ball is selected, it is then replaced in the urn before the next selection. So the required probability for same color gonna be probability of 5 choose 1 over 19. The total balls 19 choose 1 over cube. Everything is because they have 3 balls in total. They're gonna selected 3 balls in total from that each time. And then we have the answer here. That when we add them, we use the formula for the combination for no here. Yeah, we use the formula for combination over here. 5 choose 1 and the 19 choose 1, and we get this, and we do the cube.
Or you could just skip the first line because the probability won't change with the replacement. Every time because you're putting back, so the probability of choosing either color is the same. That's why you have 5 out of 5 over 19 raised by 3, 6 over 19 raised by 3, 8 raised 19 by 3, because with replacement, the probability of choosing each color stays the same. So you could
Yeah,
skip the first one. You could skip the first equal after the equal sign.
yeah, yeah.
Okay.
Thank you. Yeah,
You're welcome.
and then, yeah, and the number of now probability. So they asked two questions. It was for same color and then different color. So for same sampling with the replacement, probability of different color gonna be 5 choose 1, multiply 6 choose 1, multiply 8 choose 1, multiply 6. We can do it 6 ways for 3 different colors, divided by 19 choose 1 cube, and we get that answer.
I see. Okay. All right. Thank you, Zakia.
You're welcome.
Let me make sure give you credits. So, okay.
Hello. So,
Hello.
okay, you see me. Okay.
Yeah.
So the question is, if 4 balls are randomly chosen from an urn containing 4 red, 5 white, 6 blue, and 7 green balls, find the probability that A, at least one of the 4 balls chosen is green. So I'm gonna calculate this probability by some adding up the probability when 1 green ball is chosen, 2 green balls are chosen, 3 balls, and 4 balls. Yes, I'm going to add them up here. So the total number of balls is 22. That means by choosing 4 balls out of 22, there are 22 choose 4 ways, number combinations. Probability of choosing 1 green ball is 7 choose 1 multiplied by 15 choose 3 and divided by 22 choose 4. Probability of choosing 2 balls is 7 choose 2 multiplied by 15 choose 2 and divided by 22 choose 4. And then probability for 3 balls is a multiplication of 7 choose 3 by 15 choose 1 and dividing by 22 choose 4. And probability of choosing 4 balls is 7 choose 4 multiplied by 15 choose 0 and divided by 22 choose 4. And the sum is equal to 81%.
This is easier than finding its complement.
Yeah, I was thinking about finding the complement.
At least one of the 4 balls green. That means, okay, anyway, but this is fine. Okay, keep going.
Okay, so next question is choosing probability that 1 ball of each color is chosen. So this probability will be equal to multiplication of 4 cases. 4 choose 1, that's choosing 1 red ball out of 4, multiplied by 5 choose 1, that's 1 white ball out of 5 balls. 6 choose 1, it's 1 blue ball. And 7 choose 1 is 1 green ball. And this everything we divide by 22 choose 4. It's equal to 11%.
Okay. Anyone has any questions? All right, great, pretty good. Thank you for presenting. Anyone has any questions or anyone else like to present? Okay, Andreli, let me make you presenters and also let me.
You might be able to help.
Yeah.
All right.
Share your screen. Okay, same, I'm making you presenter as well.
Okay, I'm doing number 49. A group of 6 men and 6 women. A group of 6 men and 6 women is randomly divided into 2 groups of size.
I think we did this. I think we did this last class.
We did? Okay.
Yeah. What is the probability that the both groups will have the same number of men? Did we? Anyone remember? That's what I remembered. We did. Sorry,
Okay.
really have to choose another one.
All right, hold on.
Okay.
Let someone else go first.
Okay, same. You ready? If you're ready, you can go.
Oh, me? Yeah, I can go. Can I use the whiteboard here?
You want to use a whiteboard? You don't
Yes.
have a written down already? It'll be a little bit difficult to write on a whiteboard.
I mean, it's a pretty small.
Okay, you could try. Do you okay, you see the arrow, share content? The first choice is share black whiteboard. You could choose that one.
Yeah, I don't see that option, unfortunately.
Let me see if I
Oh,
share
I
my
see it.
web.
I see it. Yes, I see it.
Okay.
Yeah. Okay. So the question is number 49. It says that we have to choose 5 numbers out of 1 to 14, and the probability that the 9 is the third smallest value. So we have to choose 5 numbers. Wait, let me. Okay. 5 numbers out of 14. So out of 14, and 9 is the smallest value. So 9 is the smallest. Third smallest. Sorry, 9 is not smallest. 9 is the third smallest value. 9 is the third smallest. Now, in order to get 9 as the third smallest, first we have to pick 2 numbers that are smaller than 9 and 2 numbers that are bigger than 9. So in order for me to choose 2 number that is smaller than 9, I can do 8, choose 2. And then in order for me to choose 2 number bigger than 9, I can just do multiply how many numbers left? 9, 10,
Sorry.
11, 12, 13, 14. Yes.
Hold on. So 5 out of 14 numbers. 14 numbers we don't know, right?
They're 1 to 14. They are
1
1
to
to
14. Oh, 1
yes,
to
yes.
14.
They're from
Okay.
1 to 14. Yeah, these
Okay,
5
now I
numbers are
understand
1 to
well.
14.
Okay.
So
I got
9
1
is
8.
so there's like 8 numbers that's smaller than 9, and then there's 8, 9, 10, 11, 12, 5 numbers bigger than 9. So we can do 5, choose 2, and then we have to choose 9, right? Sorry, that's like that would be 1. Sorry, eraser. So this would be
1 choose 1.
this is 1 choose 1, and then we have to choose all the numbers, and then out of 14 choose 5, right? And then this calculates to be, I choose 2, 5 choose 2, 28, 1, 10, 28, multiply 10 over 2002, 2002, and then this ends up being 0.14, 0.1, and that's the answer.
Okay. All right, this could be simplified a little bit. All right, and Julie, you can do next class. All right, I need to save some time for myself. Okay, Sim, thank you to talk about some new material. Okay, thank you. Okay, so chapter 2, basically we finished, and according to our syllabus, so I'm going to save 2.6, 2.7. We don't need a 2.6, 2.7 at this moment. Maybe we'll never need it. All right, so skip 2.6, 2.7 to chapter 2. We finished, and also answer someone's question earlier. They asked me, when is chapter 2 homework due? Excuse me. I will give you one more week. Thank you. I will give you one more week to finish chapter 2 by today. So that will make, let me add it. So that's like chapter homework, chapter 2. So today is the 14th, plus one more week will be 21st. February 21st. Okay, will be due February 21st. We always present the previous one, all right? We always try to present the previous one is to serve as a review class. Don't pick the old questions. All right, so chapter 2, homework chapter 2 is due in a week. So today let's start talking about chapter 3. Conditional probability and the independence. And so far, the probability is all, the events are exclusive. It means, you know, the events have no relations. So today we're going to talk about a conditional probability. Something happened, so event 2 happens after event 1 happened already. So in this chapter, we introduce one of the most important concepts in probability theory, that of conditional probability. The importance of this concept is twofold. In the first place, we are often interested in calculating probabilities when some partial information concerning the result of an experiment is available. In such a situation, the desired probabilities are conditional because it's based on something already happened. Basically, you could think as event 2 happens after event 1 already happened. Second, even when no partial information is available, conditional probabilities can often be used to compute the desired probabilities more easily. All right. So let's think about one example. So suppose we toss 2 dice, and suppose that each of the 36 possible outcomes is equally likely to occur. And hence the probability of each is 1 out of 36, because we have 36 possible outcomes. So each one of them is 1 out of 36, and some outcomes happen to be the same outcome. Suppose for that we observe that the first die is a 3. Then given this information, what is the probability that the sum of the 2 dice is equal to 8? So you see the first event is the first die, the face value is 3. Then if we consider probability of 2 dice adds up to 8, you see the second event depends on the 3. So to calculate this probability, we reason as follows. Given that the initial die is 3 already, so the first one is fixed, and that can be only at the most 6 possible outcomes, right? Because when the first one is 3, and the second one could be 1 up to 6, right? 1 up to 6, but which one adds up to be 8? Because the sum up to that would be 8. But there's only one. Okay, so each of these outcomes originally had the same probability of occurring. The outcomes should still have equal probability. That is, given that the first die is 3, the conditional probability of each of these outcomes is 1 out of 6. Hence, the probability of the other 30 points in the sample space is 0. Hence, the desired probability will be 1 over 6. Okay. So this is just one of the examples to set us up. Now, if we let E and F denote respectively the event that is the sum of the dice is 8. Excuse me. And the event that is first die is 3. Then the probability just obtained is called the conditional probability that E occurs given that F has already occurred. So we use this notation. So probability of E happened after F already happened. So E depends on F because F is a precursor. So you make sure the order is right. Okay, E is happened after F. So if I make this textbook, I would do by the order of the character. So a general formula for probability of E happens after F happened, that is valid for events E and F, is desired in the same manner. If the event F occurs, then in order for E to occur, it's necessary that the actual occurrence be a point both in E and in F. That is, it must happen in the event of the intersection of E and F. Now, since we know that F has occurred, it follows that F becomes our new or reduced sample space. Yeah. Remember when we talk about functions, right? We usually talk about, functions can have a temporary domain. So basically, this is the same idea, right? Same idea is E happens after F happens, right? E happens after F already happened. So what it is current sample space. Its current sample space is basically F. So F becomes our desired new sample space. So the probability that event EF occurs will equal to the probability of EF relative to the probability of F. So we have this formula. If probability of F does not equal to 0, we'll never remember the 3 axioms of a probability. But for any probability, it has to be in between 0 and 1. So P of F greater than 0 basically means P of F not equal to 0, right? Not equal to 0. Because if it equals to 0, it just becomes E and F are exclusive. There's no conditional probability. Only when P of F is not 0, then P of probability depends on F, right? Equals to the probability of the intersection of E and F divided by probability of F. So just thinking F is a new sample space. And the things happening in E also happens in F because F is the current or restrained sample space. Anyone has any questions? All right, so let's see an example. Joe is 80% certain that his missing key is in one of the two pockets of his hanging jacket, being 40% certain it is in the left-hand pocket, and 40% certain it is in the right-hand pocket. If a search of the left-hand pocket does not find the key, what is the conditional probability? So what is F? F is a search of left-hand pocket does not find the key. So what is the probability that, a lot of times we don't see the word conditional, okay? But here, for the purpose of making examples, so we'll make this obvious. So what is a conditional probability? But in real life, you will never see this, right? In real life, you only see what is the probability that it is in the other pocket. Let's see the solution. So we let L be the event that the key is in the left-hand pocket of the jacket. And let R, okay, we don't use E and F anymore. So basically L is F, right? Left-hand pocket. Let L be the event that the key is in the left-hand pocket. And R be the event that's in the right-hand pocket. Then, okay, I see why they use R and L now. Then, because here we're talking about not find in the left-hand pocket. Then the desired probability of P of finding in the right-hand pocket with the condition does not find it in the right pocket, in the left pocket, in the left-hand pocket, right? Because left-hand pocket is L, find it. If the key is not in there, it's the complement of L. So the complement of L becomes the current sample space, and to find in the right-hand pocket. So there will be probability of R intersect with the complement of L divided by the current sample space, probability of not finding it in the left-hand pocket. So if in this intersection, not finding in the left-hand pocket, that's the same as finding in the right-hand pocket. So this is the intersection, right? Finding in the right-hand pocket and not in the left-hand pocket, right? Of course, if we find it in the right-hand pocket, it will not be in the left-hand pocket. So that is the same as probability of the key is in the right-hand pocket. And the probability of the complement of not finding in the left-hand pocket, that's 1 minus the probability of key in the left-hand pocket, right? Because it is a complement. This complement is 1 minus this. And this is given, what is the percentage of finding in the right-hand pocket? 40%. Right? 40% certain, which means 40%, the probability is 40%. And also 40%, right? 40% certain in the left-hand pocket. So it would be 1 minus 40%. That would be 60%. So 40% divided by 60% simplify, that's 2/3. So usually for us, the probability will be simplest form of a fraction, okay? We don't care about decimals unless it's required in the question. Right? Otherwise, we just leave as a fraction. Because the fraction talks about the probability very obvious. So 2/3, right? 2/3 is very easy to understand. Let's see these comments. If each outcome of a finite sample space S is equally likely, then conditional on the event that outcomes lies in a subset F. If F is a subset of S, all outcomes in F become equally likely. In such cases, it's often convenient to compute conditional probability of the form probability of E after F happens by using F as a sample space. Indeed, working with this reduced sample space often results in an easier and better understood solution. Let's see 2B. A coin is flipped twice, assuming that all 4 points in the sample space S, right, would be head, 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 tail, tail, head, and tail, tail. So 4 possible outcomes are equally likely. What is the conditional probability that both flips hands on heads? Given that A, so I have 2 different kind of conditions. So I consider so our E, we're considering both land on heads. So HH. And given that A, the first flip hands on heads. Okay, what is the conditional probability that both flips land on heads? Given that the first flip lands on heads, B, at least one flip lands on heads. So let B be twice, 2 flips land on heads. Then F be the first one land on heads. So that's for A, right? The first flip lands on heads. So the first flip is H, then the second one could be H. The first flip is H, but second one could be T. So F has 2 members. Be the event that the first flip lands on heads. Then let A be the event that at least one flip lands on heads. That except TT, right? Except a tail, tail. So we will have 3 members. It could be the head, 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 tail, or tail, head. So that's at least one flip lands on heads. Then the probability for A can be obtained by, remember A is this, right? But considering the E is this, both land on heads. So probability of B, both on lands on head, after event F happens, F means the first one is first flip lands on heads. So the probability of B backed with F basically is probability B, right? Because B is a subset of F, right? B is a subset of F. But sometimes B may not be subset of F. But for these cases, B is subset of F. So that's just probability of B. So probability of B. Probability of B just has one member, head, head. Then probability of F. So the first flip lands on heads. That only could be HH, HT. So 2 members, right? So probability of HH is 1/4. Right? Probability of F is 2/4. So that's just half. Anyone has any questions? Okay, let's see the second one. Second one is at least one flip lands on heads. That's this, right? At least one. So we see that's a 3/4. So we just have 1/4 divided by 3/4, which is 1/3. Okay. So this kind of questions is made it easier because B is a subset of A. Let's see C. C should be similar. In the game bridge, the 52 cards are dealt out equally to 4 players. So called east, west, north, south. If north and south have a total of 8 spades among them, what is the probability that the east has 3 of the remaining 5 spades? So we see F, right? So F is this event. And the north and south, okay, when you play bridge, the north and south are paired, and the east and west are paired. So you play, one group with fighting another group. So you have 2 groups playing basically. So north and south have total of 8 spades among them. How many spades in 52 cards? 13 of them. So then asking, so that's F. F is so A space. And then E, what's E? That's F, this is E. What is the probability that East has 3? You see, this is not East and West, only East, but this is North and South. That East has 3 of the remaining 5 space, because the 5 left, because North and South have 8, total 13, so the 5 left. So what is the probability that East has 3 space? Let's see, probably the easiest way to compute the desired probability is to work with the reduced sample space. That is, given the North, South have a total of A space among their 26 cards. There remains a total of 26 cards. Because you have 4 players, so the 52 cards. So each one gets 13. Each one gets 13 cards. So that's why East and South gets total 26 cards. So exactly 5 of them being spaced to be distributed among East and West, right? Because North and South has 8. So among East and West, total can be only 5. Since each distribution is equally likely, we always assume this though. Whenever we talk about probability, we always assume this. It follows that the conditional probability that East will exactly have 3 space among his or her 13 cards is this many. Let's see. So the sample space is out of 26, considering 13 spades, right? Out of 26, considering 13 cards, right? We only focus on the spades. Okay. Then out of 5, choose 3, because we're considering out of 5 choosing 3 for the East. Okay, what is the probability? So out of 5 choose 3. There are this many ways. Out of 5 choose 3 ways to choose the 5 space, to choose the 3 space out of 5. Then 21 out of 10. So where do we get this 21 out of 10? Well, 25 cards, right? 26 cards minus 5 spades. That's 21. So out of this 21, choose how many? Because totally we choose 13. So 3 spades being chosen. Then we're left with 10 cards to choose. So out of 21, choose 10. So this is the probability for the East side, for the East, to get 3 spades, right? So this is the event of E. And this is the event of the temporary sample space. So out of 26, choose considering this 13 cards, right? Because the North and South already have 26 cards and the A space. We just, take this out of the consideration. We're just considering the rest. So 26 cards, A space, we don't have to consider anymore. We consider the current sample space. It's the left. We think the left of the 26 cards for East and West. Right? For East and West, the total is 26 cards. 26 cards. And for the East, how many ways to choose for the East side? Now, out of 26, choose 13. Because East has 13 cards, West has 13 cards. So that's the current sample space we considered. Then, what is the probability of the East getting 3 spades? Right? There are only 5 spades left. So out of 5, choose 3. So that's how many spades East gets. But the East needs to get 13 cards in total. So the left 26 cards, choose 10 of them. So do the calculation, we should get a fraction. It will be better than 0.339. Anyone has any questions? So this is saying, if we go back to equation 2.1, the formula, right? We also get this. Sometimes if we want to find the probability of an intersection of two events, we can also do this. P of probability of the event happens both in E and F equals to this one multiply this one, right? Because this conditional probability of E depends on F multiplied by its current sample space, probability of its current sample space. So that's this one. Probability of the event, the intersection of the event E and F equals the probability of F multiplied by the probability of event E depends on F. This makes sense, right? This makes sense. So in words, this equation states that the probability that both E and F occur is equal to the probability that F occurs multiplied by the conditional probability of E given F occurred already. So equation 2.2 is often quite useful in computing the probability of intersection of events. Let's see this example. Celine is undecided as to whether to take a French course or a chemistry course. She estimates that her probability of receiving an A grade would be half in French and 2/3 in chemistry. If Celine decides to base her decision on the flip of a fair coin, what is the probability that she gets an A in chemistry? Okay, so we define some variables. Let C be the event that Celine takes chemistry, and A denote the event she receives an A. Whatever course she takes. Then the desired probability is the probability of C, intersection of C and A, right? Because C represents the event he takes chemistry. A denotes he receives an A anyway in either course. So probability of intersection of C and A would be she takes chemistry course and get an A. So the probability of this equals the probability of taking a chemistry course and then multiply by the probability it gets an A and take chemistry course. So that would be half times 2/3, which is given in the question, right? Probability of receiving an A grade, well, she takes only 2 courses that she chose from, right? So what is the probability out of 2 choose 1, which is 1/2, 50%, right? Because she either take French or take chemistry. So that's the first half. Then it's given if she takes a chemistry course, the probability of getting A is 2/3. That's this 2/3, right? If she takes chemistry course, right, that's even C, and get an A, that's this. So taking chemistry course and get an A, the probability is 2/3. So multiply those two, which is 1/3. Anyone has any questions? All right, let's see next example. Suppose that an urn contains 8 red balls, 4 white ones, and draw 2 from formula without replacement. With replacement, the probability stays the same. Okay, without replacement, the probability changes. 8. P of C equals a half because the P, one side of the coin equals the half. Oh, okay. You could think that way. Oh, yes. Hold on. Probability of taking C. Yes. You could think about like that. This actually, even the question saying on the flip of a coin, right? A fair coin. Or you could just think from here. You know, he only has two courses. She only has two courses to take. You know, she flip a coin. Maybe she names a head. Okay, if it's landed on head, I'm going to take a French. If it landed on tail, I'm going to take a chemistry. All right, you could think that way. Right? It really doesn't need this. It really does not need this. But anyway. Okay. So A, if we assume that at each draw, each ball in the urn is equally likely to be chosen, what is the probability that both balls drawn are red? B, now suppose that the balls have different weights, with each red ball having weight R, and each white ball having weight W. Suppose that the probability that a given ball in the urn is next one selected. It's the weight decided by the sum of the weights of all balls currently in urn. Now, what is the probability that the balls are red? Okay, very interesting. So A is considering the outcomes has equally likely, okay, weight. And the second one is saying the weight for choosing, so the outcome is not equally likely to occur anymore. So this we're putting on, put on weight, you know, has ranks now. So choosing a red one has weight R. Choosing a white one has W. Okay. So then we consider the same thing. What's the probability that both balls are red? Okay, let's see this. So let R1, R2 denote what it denotes. The events that the first and second balls drawn are red. Okay. The first time is red, second time is red. Now, given the first ball selected is red, there are 7 remaining because no replacement. Right. A 7 red and a 4 white. Right. So that means the probability of choosing the second one to be red with the first one is already red. The first one is already red. It's just out of one choose one. And then we are left with 7 red ones and totally 7 plus 4, 11 balls in it. So that would be 7 over 11. And probability of choosing the one to be red, how many? We have 8 of them, right? A over 12. So probability is A over 12. Then the desired probability of choosing the first one and the second one to be red. Right? The event of the first one is red and the second one event is red. A second one is red. So the intersection of these two events will be probability of R1, the first one, probability of the first one is red, and multiply by the probability of the second one is red, depends on the first one is already red. So that would be probability of the first one is red is A over 12. A over 12 simplify, that's 2 over 3. With the conditional probability, where the first one is red already, we choose the first one and the first one is red. And the probability for the second one is to be red is 7 over 11. 7 over 11. So multiply those two, get a 14 out of 33. I hope you see the difference of this one and with the previous one. The previous one is a subset of the first event. The second event is a subset of the first event, right? Here is just different settings. Has different settings. Anyone has any questions? And this is saying, of course, this probability we could calculate it this way. How do we calculate it? We'll calculate, okay, out of 12 balls, we're choosing 2, right? That's a sample space. And what's the event? The event is out of the A red ones, choose 2 of them. Right? So total we have A red ones, choose 2 of them. That would be out of A choose 2 divided by out of 12 choose 2. The answer should be the same. For part B, all right, so what is part B? Part B, we have to consider the weights. We have to consider the weights. And we're going to use this one. So number the red balls. We have 8 of them. So we have B1, B2 up to B8. So the first one, choosing the first one is red, is probability of the union of, so this is B1, B2 up to B8, right? So probability of all this. So that is probability. Well, probability of all those, the sums of all the sum of the probability of choosing each red ball, right? Choosing each red ball. What is that? How do we calculate? Let's remember the red ball has a weight of R, right? So we have R divided by what's the total weights. We have A of the red ones, we have 4 of the white ones. The white ones have weight of W, so we have AR plus 4W, right? So it's R divided by AR plus 4W. And for the A balls, they'll be equally likely. The outcomes, choosing either to the one of the A balls will be equally likely to happen. So that's why I have A multiplied. Right? So the probability of B1 equals the probability of B2 equals to probability of B8. So there will be A multiplied by R divided by AR plus 4W. Now, given the first one is red already, right? Given the first one is already, and we only have 7 red left, and we still have 4 white balls. So what is the probability of that? There will be R divided for each one of them, right? P of all those B, BI's, but only I up to 7 now. So it would be R divided by 7R plus 4W. How many of them we have? I have 7 red balls left, so multiply by 7. So the second ball to be red depends on the first one is already red without the replacement. Even with replacement, the probability would be the same without replacement. So the second ball is the probability is this. So now we can find the probability of the first one is red and the second one is red. Right? Would be P of R1, probability of first one is red, which is this. And the probability of the second one is red, it depends on the first one is already red, is this. Just multiply those two. Anyone has any questions? Multiplication rule. So probability of all the intersections of all those n events. Yeah, we could do this. We could use the formula 2.2. Where P of E1 times P of E2 depends on E1, P of E3, so on and so forth. So E3 depends on E1, E2. Then En depends on first n minus 1 events. It's called the multiplication rule. In words, the multiplication rule states that the probability of the intersection of all n events is equal to P of E1, the probability that E1 occurs multiplied by probability of E2, depends on E1, the conditional probability of E2 occurs given that E1 has occurred, then multiplied by E3, the conditional probability of E3 occurs given that both E1 and E2 already occurred, so on and so forth. So to prove the multiplication rule, we can just apply the 2.2 formula into this. Then we see the simplifications. Right? Let's see an example. Okay, next class we'll talk about Bayes' formula. Very important formula. Okay, let's see this example. In the match problem stated in example 5M of chapter 2, I don't remember the example, it was showing that at Pn, the probability that there are no matches when n people randomly selected from among their own n hats. Oh, okay. Remember the tossing the hats? You know, a room of n people. You know, they all have hats. Tossing the hats to the air. Then how many of them, you know, getting their own hats are probably like that. I mean, situations like that. So this is saying no matches when, which means nobody catches his or her own hat probability. The probability that there are no matches when n people randomly selected from among their own hats. No matches means no one gets his or her own hat. Is given by this probability of n equals to I goes from 0 up to n, -1 raised by I divided by I factorial. What is the probability that exactly k of n people have matches? So exactly k people caught her and his own hat. Anyone remember this? I don't remember. I don't remember probabilities like that involve -1 raised by I divided by I factorial. Especially I don't really remember the proof of this. It'll be a good review to go back to see this. But for now, let's see. So let us fix our attention on a particular set of k people and determine the probability that these k individuals have matches and no one else does. Letting E denote the event that everyone in this set has a match. And letting, so this set of k individuals, okay. So E be the event, you know, k individuals have their own hat. And letting G be the event that none of the other n minus k have a match. So we have probability E intersection with G. So E denotes the event that everyone in this set has a match. And the G denotes the event that none of the n minus k people have a match. So probability of even E intersect with G equals the probability of E, even E, multiplied by probability of G happens, depends on E already happened. So E is an event everyone in this set has a match, right? And G is the event none of the n minus k people have a match. Because we don't know how many, we don't know how many in this. This is not defined on k, okay? The E is not defined on k. E is defined, you know, event everyone in the set. We're not sure about this set has a match. Then this makes sense. Otherwise, this wouldn't make sense. So now let I goes from 1 to k be the event that S member of the set has a match, right? F1, F2 up to Fk. So probability of the event E would be probability of the intersection of all those, because everyone. So now this E is related with K. So this means all those k people have their own match. Then use the formula 2.2. A probability of F1 times the conditional probability times the conditional probability times the conditional probability. That is, out of 1 we have n, out of 1 have 1 minus 1, out of 1 n minus 2, so on and so forth. The last one will be out of 1 n minus k plus 1. That's how many people left, right? Because the first one is we have n people, n minus 1, n minus 2. The last one would be n minus k plus 1. And this we can simplify to be n minus k factorial divided by n factorial, right? If you simplify this, you can see you get this, right? And from this to get this is not easy. But if you do backwards, right? If you write this out in the backwards, you see clearly that's this one. So everyone in the set K has a match. That's the condition given. Then the other n minus k will not be randomly chosen among their own n minus k heads. So the probability that none of them has a match is equal to the probability of no matches in the problem having n minus k people chosen among their own n minus k heads. So we have this. So no one, so in the n minus k set, no one has a match. So probability of G depend on probability of E. Remember, probability of E is everyone in the set gets their own. Everyone in the set has a match. And G is none of the other n minus k have a match. So probability of the n minus k, right? None of them have a match. When the k people have matches already, is the probability of n minus p of n minus k. So this notation is this, right? So we want to use this formula. So we need to remember this formula. So when we have n people and none of them have match, that's this formula. So now we have n minus k. So we just use this formula. So I goes from 0 to n minus k of -1 raised by I divided by I factorial. Now we can find probability of E intersected with G. Probability of E intersected with G is n minus k factorial divided by n factorial, which we simplify from this. Probability of E, right? Probability of E multiplied by probability of E. G happens, depends on E happened already, right? So probability of E multiplied by conditional probability of G depends on E, which is this, which is this. Because there will be exactly k matches given in the question, right? And so out of n choose k many ways, right? Out of n choose k set of k individuals. Then probability of exact k matches equals to p of intersection of E and G multiply how many ways of choosing these k individuals to form a group. That's out of n choose k. So if we do the calculation in the end, we get E raised by -1 over k factorial, or 1 over E, right? 1 divided by E divided by k factorial. So this E we can leave in the denominator. The numerator is just 1. 1 over E k factorial. Classic question. Anyone has any questions? All right, so next class, when you like to present, you can present 2.5, right? Ideally, you present 3.2. Ideally, you can present 3.2, but you can also choose some interesting questions to present for 2.5, all right? Anyone has any questions? Conditional probability is very useful in life. Things like this, we just have to remember, all right? We just have to remember for this course, for this. All right, that's it for today. And anyone has any questions? I'm going to stop recording.